Okay. Well, the first thing we have is a frequency table of divisions, number of respondents that were in that division, and this is the entire set, and then the collapse division, just so you can see them back to back, what they look like before and after. There are still um, some groups here that only have 2, 3, 4. That's pretty low, but I don't know that it's worth taking them out at this point. Just go ahead and leave it in. Maybe mention it in your limitations. It does come into play a little bit later when we run the ANOVA, and I'll mention that. And then here's some descriptives. I think you should have these anyway, but just wanted to make sure. So years of servedness, and then we are treating all these as quantitative now. So we have means and standard deviation of these four variables. Okay, next thing we have is the Pearson correlation coefficients. It's a matrix if we click this here. So you can see that there's three, any combination of those four quantitative variables are found somewhere in this chart. Let's just take one, years of service and behavior. So these three numbers for years of service and behavior. Again, correlation, so it doesn't matter which order they come in, these values will be the same. And that's why the matrix does not have one down here for years of service and then behavior here. It would just be redundant. So we only have the 6 possible combinations that any two of the four together. So behavior with years of service or years of service with behavior, no difference. And either way you look at it, there's a slight negative correlation, negative 0.015. What does that mean? Well, not a lot. I mean, it looks like there's really not much correlation at all. It's certainly not statistically significant. It's not anywhere close to that 0.05 cutoff level. But it is negative. So how would you interpret a negative? The more years of service a respondent had in your survey, the lower they tended to score on the behavior subscale. But that was a slight difference. And just as a reminder, if you wanted to use that in some kind of mathematical situation, let's take this 0.06 here. It's a little bit higher. This is an R value, Pearson correlation coefficient R. Remember, you cannot convert that to a percent. That would be meaningless. What you can do, if you want, in your results discussion, you can square that. So you'd have 0.06 times 0.06. So 0.06 squared. And that can meaningfully be interpreted as a percent. So in this case, it would be, we would move the decimal over 2 spots for decimal to percent conversion. Then that would be 0.36%. So that says, there were different levels of years of service in your study. And we can say that 0.36% of that variation in years of service was somehow connected to knowledge, or much more, I mean, that's legitimate. Much more meaningful would be, okay, the nurses in your study scored different on this knowledge subscale, right? So there was variation there. And the question is, why the variation? Is it related to their backgrounds? Is it related to socioeconomic status? Is it related to their experience, years of experience? Well, we can say that 0.36% of the variation in knowledge subscale can somehow be connected to, not necessarily caused by, but somehow connected to, associated with, correlated with their years of service. Which, to be frank, is not a lot. That's saying that 99.6% of the variation in knowledge is somehow connected to other reasons. So to me, that's saying that the years of service isn't really that good of an indicator. And we also see that backed up even statistically. So that would be more of a practical significance measure. Again, this one's not statistically significant either. So are any of these statistically significant? Well, this one is below 0.05. So the more knowledge they had, the lower their attitude tended to be, and the more the better the attitude, the lower their knowledge tended to be. I think knowledge first and then attitude would make more sense. Um, but you also have to keep in mind you're running 6 different correlations here. So if you do any kind of Bonferroni correction or anything, this still probably would not show up as statistically significant. So Bonferroni, again, is that 0.05 divided by the number of tests you're running. So if you're just kind of looking for any of the relationships in these 6 possibilities here, you should take 0.05 divided by 6, which would be a little less than 0.01, and that would be your threshold. That would be your cutoff for statistical significance. So if you decide to do that, which is the more statistically accurate way to do it, then we would no longer have a statistically significant relationship between these two. However, this one would hold up between knowledge and behavior. So certainly it looks like the more knowledge that the nurses in your study have, the more they tended to act upon that knowledge that there were behavior towards the immobilization. Okay, so that's one of your main results. Then we have some descriptives here. I put in 2 tables just to make, I mean, it was only an extra minute for me. So these are the collapse divisions, and either way, you're going to have the mean and standard deviation. I didn't know if you wanted the min and max. You have to be a little careful because the min and max on a very small sample group is going to be much more tightly together than for a larger group. So I'm not sure how meaningful the min and max are. The mean and standard deviation are, of course, something that should be in there somewhere. And so this is the chart you may want to end up using here. And this would also have the number within each one. So this would give you a lot of data here. And if you want, we could try to think through putting this in a chart too. If you try to conceive of a chart that you might like to do to show this data instead of a table, let me know and we could. Okay, so then we have some more stuff there. I did want to give you a visual on how these correlations play out. So here's years of service and knowledge, and you can see that there's not a really strong linear correlation there. Like even going up into high years of service, no matter where you are in years of service, you're mostly between 3 and 5 average on the knowledge subscale. And then did similar things for attitude subscale. Again, not a lot. You could, if you want, discuss an outlier. There's maybe an outlier. There's maybe an outlier there, but not a lot to talk about in any of these. Okay, and then I'm not sure you would use this, but again, it was easy for me to throw in the output. This is a correlations matrix. And like I said, we have the 6 different correlations. So we'll see those showing up down here in the bottom left and in the top right, just like we saw in that chart that we talked through for. And so if you look at years of service and knowledge subscale, for example, this chart right here, you can also look at years of service and knowledge subscale. So these two right here are the same thing. They're just flipped. You can almost see that it's rotated. So you really don't see a lot of correlation there. You do see the knowledge behavior, which was the strongest correlation. You can kind of see that positive line going through there, but you may or may not use that correlation. Okay, then we have the specific items that you wanted to look at. So here's those 4 items along with years of service, and again, just put in some descriptives. Here we looked at these are the Pearson correlations. So this would be the parametric version. The interpretation would be just like we did up there in the previous correlations chart. And then these are the non-parametric versions, which so for the entire subscale, like we talked about, we have Likert scale, which we're treating as quantitative, and I think you have good evidence for that. When we talk about Likert type items, so that's just the individual items, it might make sense to do a non-parametric Again, it's hard to say. There's no set answer. It really depends who you're dealing with. You kind of do what you. Um, so here, statistically, this would be the more statistically appropriate thing to do. That the purists would like to see this better. Here we have Kendall's tau, which is essentially, you can think of it as the same way as the Pearson correlation are. You can interpret the statistical significance again. So here, years of service does seem to have some correlation there with the nurse to patient staffing. So the more years of service, the more they tended to say that the staffing was adequate for mobilizing inpatients, and vice versa. The fewer the years of service, the less likely they were to say that. So here's where we get into the ANOVAs. Remember the basic premise of an ANOVA. It's an extension of a t-test. So it's basically looking at more than two groups, and we want on some outcome that's quantitative, and we want to know that the null hypothesis is that the means are all the same. They're all exactly the same. The alternative hypothesis is that there's a difference somewhere in the means. Now, here's where, because you only had, or because not only, you had 10 groups, which is a lot for an ANOVA, you can see here that the degrees of freedom were 9. It's one less than the number of groups. You can also see this is the p-value for the overall ANOVA test. So when you do an ANOVA, you first run an overall, which basically says anywhere along your group means, is there anything that's strong enough different in the sample that we're pretty sure it would be different in the population as well. And it could be that the mean of group 1 is higher than the mean of group 9, and all the others are exactly the same. Even still, that would trigger a statistically significant ANOVA. So when you think about 10 groups, the chance that there's some difference in means along the way somewhere is very high. So I'm not at all surprised to see a low. And this, by the way, is not 0. This is, you would put p less than 0.001. It can never be 0. This is just rounded to the nearest thousandth. It's still 0. Whatever that number is, you would put p less than 0.001 for the overall ANOVA. And I believe you probably want to report these two numbers. Maybe look in the literature how your ANOVA results are reported and follow that practice. So after you've found that there's an overall significant result, that's when you dive in. Now, the first ANOVAs we see are all for the knowledge subscale, and then we'll do the same for the behavior and the attitude. So what do we have going on here? Well, we have a lot of stuff going on here because we have 10 different groups, and now we're doing what's called a post hoc test. So, okay, we found a difference somewhere. If this was not significant right here, then we shouldn't really go any further. There's not too much point in going further. If we do find significance here, then we drop down to the multiple comparisons, and we're looking for a difference between group 1 and group 2, division 1 and division 3, division 1 and division 4, and then we go down here, division 3 and division 5, and so on. In each case, we're getting how far apart were they. Remember, we're on the knowledge subscale, so let's just look at one example here. So divisions 1 and 2, and I think they're alphabetical order. Hopefully up there I put the number somewhere. If you don't see a code, they should be alphabetical order, the 10 class divisions. So if you need help with that, just let me know and I'll send you that list. But this would be saying between divisions 1 and 2, and specifically I minus j. So division 1, on average, had 0.053 points higher than division 2 on the knowledge subscale. Here's our standard error, our p-value for that difference. Is that difference strong enough between the two sample groups that we think it exists in the population? And then where are we pretty sure that mean difference lies? Our confidence intervals. So as you can see, it could be group 1's higher, it could be group 2 is higher in the population. which is why it's not statistically